All right. Announcements. We have a homework due tonight. And given what I've added, the complexity that I've added to it, I am intrigued to see how that is going. That made everything significantly more complicated. And I think that it's really good experience, but I also recognize that it's very difficult to get working. So that is something that I am aware of. It's something that I will account for. As I've told everyone how I grade in this class is I go look at grades at the end of the quarter. So even if a single assignment doesn't go so well for the entire class as a whole, if the grades that people have at the end of this course do not align with the effort that I have seen, and because I hold so many office hours, I think I get a pretty good view of how much effort people are putting into the class. I see a ton of effort going into this class from just about everybody's perspective. So that helps me to have a gut or a reality check of, do these grades match the effort that I have seen? If they don't, I will just curve them up until I'm happy with them. So I think that worrying about grades will not serve you as well in this class as it does in other classes, because I'm trying to advocate for you and have your best interest in mind at the end of the class. Question? Yeah, we need to do it with something. So the point of the pivot is that at the end of a particular outer loop of quicksort, we need to know for sure where one element goes. And if we didn't have the pivot, it's kind of a baseline. What are we comparing every other element in the array to? So I guess maybe the best place to start is if you were asked for a one sentence summary of quicksort, rather than going into the detail kind of that we have, you would say, pick one element, put it in its relative place by putting everything less than it to the left of it and everything greater than it to the right of it. So the point of that pivot is to make sure that we have that element that we compare to. Here, everything else in the array to. Less than just goes somewhere at the beginning, greater than just goes somewhere at the end. So what can I draw out that helps that to make sense? Yeah, so by itself doesn't really answer that question, I feel like, but what is there a follow-up of a particular element of that process?
I understand, like, if you compare the pivot with, like, because you want numbers to go on the left side, right? So numbers that are less than the pivot, I think, go to the left.
Far left, yeah.
Side. You want the numbers greater than the pivot than our right side. I think that's where things are confusing, because you know that you're gonna compare them, right? You're gonna compare like data from like your array list, right? With the pivots data. And I think it's just the moving it to the left side.
Yeah, that is very much the hard part, is where do we move things? And normally you can just easily keep track of an index and swap. We can't bump that index down in a singly linked list.
Yeah, that's where I'm struggling, because I don't understand where to move left side, because I know that it's current, or in my case, it's current dot data, and then dot compared to pivot dot data, and it's less than 0. So if I know that numbers are going to be less than, so they're going to move to the left, but I can't figure out from
Yeah. So what I said in class last time, what you want to do when you see something that's greater than, you want to identify, I've done something, and move that to the end. So you're going to add a copy of that to the end of the list, and then delete that from the list. That is the equivalent of, it's not quite swapping it because nothing is taking its place. Everything else is moving forward one, which would be very ineffective in an array or an array list. But with a linked list, that is a very simple process of just deleting a node. And now that means everything that came after it is one index closer to where that node was. So does the effect of getting things that are larger than the pivot to the end. Once we've done this a number of times, equal to the number of elements in the list, then we know how many elements are greater than and less than the pivot. That's what we're keeping track of. Yeah, yeah. Yeah, depending on whether we do something or not. If we move a node, prev is still pointing to that previous element because we got rid of where prev would move to. But if we didn't do that, if we didn't move anything, then both cur and prev need to move up one. Let's draw out a quick example of that because I think that should be seen visually. Question in the meantime?
It's the time it's supposed to take to sort like 10 million elements to be long.
It is, I said 1 million will probably get you within a few seconds. If it's 10 million, you might have to wait a little. But if it finishes, even 10 million finishes within a minute, I would say that's probably good. If it takes significantly longer than a minute, then that's not good. And if it's quadratic, then it should certainly be taking longer than a minute at that point. If it's quadratic, it's about half of the quadratic. If you square 10 million, a million times a million is a trillion. And even if something can do 5 billion calculations in a second, that division gives you 200 seconds. So it's still 3 minutes and something. I think it's actually still longer than that for this. And that's just 1 million. 10 million is going to be even worse. So let's just quickly draw out an example. Four elements to show Saxon's point. So we have some pivot, no matter what it is, 72, and we'll have some elements that are larger than, elements that are smaller than, or an element that's smaller than, and an element that is larger than. So if this is our pivot, what I'm saying, what I'm arguing will solve this process is that this is going to be our pivot. We're going to start this out as what we're going to call prev, and we have another curve that's going to point at the next. We need to, for the number of times that is the length of this sublist, because remember this isn't the entire list once you recursively call this. So we still need to figure out how many elements are in this sublist. If we can figure that out somehow, then we know how many times to do this process. We want to do it the length of this list minus 1 times. Is compare cur to pivot. Is the list at cur and the list at pivot. If the list at cur is larger, we're going to delete it and add it to the end. So we will do that. We're going to move this over there, which redirects this pointer past here. When we do that move, as we can see, prev is still pointing to the previous element to the new cur. We just needed to bump up cur to now point here. When we deleted that node, prev is still the previous node to cur. We now ask, is cur greater than pivot? It is not, so we bump it up. It's the list at cur, I should be saying. Is the list at cur? If we didn't do anything, we also bump up prev. And we've done something twice, so there's only one more time to do this. So is cur greater than pivot? Yes. So we're going to add it to the end of the list and delete it. So this is now going to go to whatever this pointed at. So we can see everything that was larger than this got deleted and re-added. There are 2 more nodes, 104 and 77 out here. So we did something twice. What does this tell us as to where the pivot is supposed to go? Now, what I had said is we count up from pivot, but we should be finding this size of this list, which we said is 4. We should be counting back from it. So the number of changes that we made, 4, 3, 2, or rather, you don't want to start at 4, you want to start at the list size minus 1, because it's the last valid element in the list. So starting at 3, so you have 0, 1, 2, 3, that's basically the indices here, because 0, 1, 2, and 3. So you start pointing here, and every change we made look back and back. And or it's wherever prev is. That would be the even easier way to do it, as I'm going to argue. I think this is always where prev is after this process is done. And that is where the pivot should be swapped to. So now rather than changing any of the structure of the list, we're just gonna swap what's in pivot and what's in the list of prev. So we swap the 72 and the 48. And then this is locked in place, just like quicksort has said that it is. This is in the right place. And we have to recursively call quicksort now on this sub list and this sub list. So I think that gets us to where we need to be. Questions or clarifications on that? Curious to see, has anyone gotten it working to this point? One person? Two people? Have you tested that it's working in log linear time? Yep. All right, I'm gonna be busy today. I think this is a good work. This is very good work, but as I've mentioned, this is a very difficult thing to get working. So let me help you to get that process working, and I will tell David to be a little bit nice in the grading of this, because this is not easy. Anything I can clarify? Yeah, clarify before we start. I would focus in on parts of the list. The issue with that you're going to come into with that, I do think you're going to end up having to copy it, thinking about it, because if this is a part of the list, you don't want to be adding to the end of the list, because where is the end of the list? How do you, because this last element isn't actually going to be null when you call it on some other prior chunk. So yeah, we will have to make a single pass and go through and copy it into a new structure that we can mess up. And then when you're done, you'll have to copy it back. But that said, that's still going to be linear because you're doing it once.
So we just swap the value of prev and pivot, and then we need to return the high index minus the number of changes.
Yeah, high index here being 3 minus the number of changes should be exactly the function you need to grab the index. So I will certainly have time to help you with this today. I got everything that I needed to get done on Friday done. 7 minutes to spare. So I have some more availability today to help out. But in the meantime, we have something to do to help you prepare for algorithms, because I believe you implement this in algorithms, and it's really important. I don't want to just talk about the simplest data structures. I want to talk about as many of them as I can get through, and heaps are important. So anything else before we get started with lecture stuff? Other reminders, we have an exam on Friday, but heaps will only be covered at a high level. So you won't be asked to do anything with heaps on paper, not to code anything. Yeah.
Will you post the second guide for the test today?
Should be up.
Can I just not see it?
Right after class on Friday, I went back and revealed it. So my apologies on that. Hopefully people saw my announcement that I extended the assignment to today, because that's, sorry. Those Canvas notifications are important. So we talked about inserting into a heap last time. Do we remember that? So rules of a heap, it's just visualized as a tree structure, implemented as an array-based structure. In this tree structure, every node is greater than all of its children, and because that rule is applied recursively, then it's true for all of its ancestors as well, not just its immediate children, but it's greater than all of its ancestors. We don't have to check that. The second rule is that the heap is full for every level aside from that last level, and that last level, every node that is in it is as far left as it possibly can be in that tree. And this means that we can store it all in an array. a contiguous array with no blank or no values. So to insert, we said that we look for the next open position in this heap, which is going to be the last level as far left as we could insert a new node. When we do that, we've likely violated some of the heap properties. So to do that, we're just going to recursively compare the newly inserted value with its parent. If it's greater than, then we're going to swap them. And then we do it again, compare with its parent. If it's greater than, swap, compare with its parent. If it's greater than, swap. As soon as that is not true, you can just stop. It's in the correct place. And that is guaranteed for all heaps. It is also guaranteed to be logarithmic for a single insert, which is extremely nice. So we took an example of one of those. How do we feel about inserting into a heap? Just to get a sense of, we drew this out on the board last time, should I do it again? How do we feel about inserting into a heap? Okay, one more example. I agree. All right. I'm gonna need some values to make this a legal heap. It's something. Yes, yeah, we'll implement a min heap when we go code it. We're still gonna think about it in terms of a max heap. But starting at the root and moving down, kind of in a level order, let's get some values. Are there questions before we do that? Or values? 100. Start with 100, sure. What else can we add to this heap? What goes here or can go here? 70 seems reasonable. What can go here? 1, 2, and 3, you say? 3, and 1 and 2? 123. That would be greater than 100. We can't have that. Something that's less than 100. 10, that'll work. What could go here? 55. 55 seems reasonable. What could go here? 30. 30. Sure. What could go here? 87. Less than 10? 7. 7. You go here? 3. That is true. What could go here? 13. Sure. That is a legal value. What could go here? 25. 25. And what could go here? 16. All right, I agree. This is a legal heap. Let's say we want to insert something into this heap. What value do we want to insert?
8.
If we insert 8, it goes in the last row, leftmost position that it could go in. So not a left child or right child of 7 or a left child or right child of 3. It should go here. So we're going to compare it to its parent. Is 8 larger than 30? No. We finished the process, it is already inserted. Does that mean that this is a legal heap structure? Yes. We don't have to do any more work, it's legal. What else could we put in here that would cause us to make at least one swap? 42. Before we start, legal heap? No, it violated one of the heap properties. So 30s, all of its ancestors should be less than it. 42 is not less than 30. So starting with the position of this inserted node, we ask, are you larger than your parent? The answer is yes. So we swap them. Recurse. We're still at this 42. Is 42 greater than 70? No. Now we just stop the process. The insertion is finished. The heap should be legal. And it is. But if we inserted something like 1,000, you would see we would swap, swap, swap. And it would end up at the root. And that would be okay. That entire process would maintain the heap structure. How do we feel about inserting? Does that process make more sense? Always start in the lowest leftmost open position. And then just query for that position. Parent, 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 parent. So if you have this structure, it's likely you'll want to figure out either where this is, if it were stored as a tree structure, but this is why we store it as an array structure. Where is this in a tree structure? We have to go figure it out. How do we figure out where it is in a tree structure? That would be an interesting question. From the root, we visit the left child or the right child to go find that last place. We don't know. We don't know where it is when just looking at the root. It has 2 children. So we have to go explore both of them. To go find where that next open position is, it's a longer process. If we're storing this in an array, how difficult is it? The next open index, we can just call add. So it takes what would be, I don't know, is there a logarithmic way to do that? To find this? I think there actually is. I think you end up querying in a queue. So you would put the 70 and the 10 on the queue, you would put this on the queue. And yeah, that's still gonna be, it's linear, but it's half the number of nodes to figure that out in the worst case. But yeah, with an array, it's constant. That very last element that is, the next element that's open, you add at the end of the array, done, constant, count a spot. So insertion into an array, much easier. I'm gonna have to draw out another one of these because we're gonna delete from a heap. Deleting from a heap is actually very easy because we don't allow for arbitrary deletion. We only allow us access to the largest element at one time. And this makes sense when I told you about the concept of a priority queue, where we want to take out the element that's been in there the longest that has the largest priority or the highest priority. So if we ask where is that element's going to be at the root. So deleting means that we just have to do something with deleting the root. But what does that process look like? Let's see if we can invent this algorithm. I'm going to draw this thing larger. The last one I drew was too small. Let's see. We have a heap. To delete from this heap, you can only delete the root. So we're going to return 120, but we have to change the structure of this so that it is still a legal heap. What do we want to do that? Can anyone think of what that algorithm might look like? Yeah,
I want to start by checking both these children and see which is greater.
okay. So starting and checking for which of these children is greater, identifying 63, what do we do with the 63?
Make that the root and then reinsert 44.
So do that and then reinsert this. Now this whole thing is still, since we know this was the greatest child, we know it's already in place. But then we have to query which one of these is greater, which one of these is greater, but then we violate the whole leftmost element of anything from there. That's what's going to be challenging with that. That is the second half of the algorithm, the second part of it. There's one thing we need to do to prepare for that, Dan, so that's really cool to see. What we're going to do is we're going to swap the root with the last element. So we're gonna start by swapping and saying this 120 goes here, this 3 goes here. When you do this, we can safely remove the 120 from the heap. It's gone. But just like with insertion, we violated the heap property. But luckily, it's just the one heap property. So now we can take Saxon's algorithm and apply it. So we're going to compare 3 with its children and say, which one of these children is larger? And is that larger child larger than this node? So is 63 larger than 44 and 63 is larger than 3? Is 44 larger than 63 and 44 larger than 3? The first one of those is true, the second one of those is false. So since the first one was true, we're going to swap the 63 and the 3. We recurse on that node. We're slowly just bumping the 3 down and replacing it with something that's going to make everything above it look like it's a legal heap. So comparing the 3 to its children, which one is larger and is the largest child larger than it? 50 is the largest child and 50 is larger than 3, so we're going to swap. Recursing, is 3's largest child larger than it? 3's largest child is 19, 19 is larger than 3, so we're going to swap. What are the most number of swaps we will do in this entire deletion process?
The depth of the tree.
Yeah, it's the depth of the tree, which we know is logarithmic with proportion to the number of nodes stored in the tree. So because of that, this is a logarithmic time delete. It's constant to swap that with the largest element or the last element in the heap, because we know it's stored in an array. Where is that last element held? At the end of the array. We can make a swap for free. And with an array, we can easily delete at the end without having to move anything else where it needs to go in the array, which is what we know is the weakness of using an array as a structure anyway. So this allows us to make the swap constant, the bubbling down. We're going to start calling this what? Heapify down. We have heapify up that we do in an insertion and heapify down that we do in a deletion. But it makes each of them logarithmic because we are making a number of comparisons and swaps that are at most the depth of the tree, which is logarithmically proportional to the number of elements in the tree. So because of this, deletion is also log n. Questions on the deletion process? Does that make sense? So that's basically the deletion process. I'm sure I just revealed this entire slide, or just did this entire slide with the word. So where is the max element? It is at the root. To delete the root, we swap it with the last element in the heap, which is what we just did. Store the value from the old root, delete the node. So we would store off the 120 so that we can return it at the end of the deletion, because that's what we want to do with any structure that we delete from. Since we violated some heap properties, we will set that current node that we found as the new root and loop heapify down. As long as the child is smaller than at least one of its children, swap the current node with its largest child. Repeat that process. After we've done that, do we have a legal heap? And the answer should be yes. Complexity for that, we just talked about it. Deleting is also logarithmic. Everything that we just said. Questions on deletion? How do we feel about it? Can you set thumbs? All right. Seems good, seems better. So why would we care to, aside from a priority queue, we talked about a priority queue and being able to now logarithmically insert elements into what we might think of to be something like a task list. That allows us to now, with constant time, access what is the highest priority element, and logarithmic time, either add a new element to this list or remove an element that we've completed. And of course, we would only ever complete the most important thing in our task list. So it is a priority queue. I know I expect a lot of people, don't I? One other thing we can do with this, I hinted at this on Friday, was we can actually sort with a heap. So heap sort uses this concept of a heap to sort a list. So we know since we're storing this in an array already, all right, well, what could we do in order to sort this list? How could we use a heap to do this? So we have an unsorted array. First question we might ask is, well, we need to turn this array into a heap. How long does it take to heapify something that is randomly sorted? Randomly structured, I should say, not sorted at all. What do we think? What process would we use to turn a unsorted list into a heap? That would be amazing. On an individual element basis, we can get that. That would be nice. It is log linear. And the process we're going to use for this is we're just going to insert every element in the array into the heap. How many elements are there? Linear based on the size of the array. How long did it take to insert something into a heap? Logarithmic based on the size of the heap, the depth of the tree that is represented by that heap. So we get a log linear heapify. All right, now we're at a heap. Where is the largest element? It's at the root. So we can remove it and put it in the last position in the array, because we know that's the largest element in the entire array. That's what selection sort took a linear amount of time to tell us. But now that query is constant, given that we underwent this heapify. Great. If we successfully delete that element and restructure our heap because of that delete, where's the next largest element? At the root of the restructured heap. So deleting took a logarithmic amount of time to get that largest element. It's a constant amount of time to put it in the last position in the array. So we just repeat that logic over and over and over and over. A linear number of times, we will delete from the heap, put it in the next largest place in the array, delete from the heap, next largest place in the array. Continue that process, and that's log linear total. So we have something that is log linear followed by something that is log linear. Total amount of time, log linear, since we're doing them successively and not inside of each other. So that's heap sort. It actually just uses the heap structure, and it's not very much code at all once we have the heap working. So we're going to start talking about implementing it. So we're actually going to go do this together. We're going to implement the heap object, and then we're going to write a heap sort based on that heap object. So rather than have you break into groups and try to implement it, we're just going to go do it. Down to our 4 files, I need to go fix them and make sure they can find.
Does heap sort like a algorithm produce a reverse sorted list?
No, it'll actually it could if you started at the beginning of the array and filled out. Or if you start at the end and fill back, so you know how many elements there were in the list before you started, you know where to place each one of the largest elements. So it'll produce a sorted list starting at the end of the list and backfill it toward the beginning. Let's see. I actually think I want to do this in sorts. Let's do this in sorts. We'll make a new sort. Let's make a min. So we've talked about a max heap is every element is larger than all of its descendants. The only difference between that and a min heap is that a min heap is the smallest element is found at the root. And every element must be smaller than all of its children, smaller than all of its descendants. So both of those will work, both of those will produce that same behavior. It's just a matter of how your priority is described. If a high number means it's very important, then you want a max heap. If a low number means it's very important, then you want a min heap. But they're both exactly the same structure. So it's very small. Okay, so we're going to be able to do this. We again want it to be generic, so let's go add our T extends comparable T at the beginning. What were our fields? What do we need to be able to store for a heap object? We need to know the underlying array that we're storing it in. Since we're not storing this as a tree structure, we're storing it as an array structure. So it's going to be an array of T's. You could make this an array list of T's if you wanted to. Doesn't really matter. We need to know how many elements there are in a heap. So we will make a size. And since we're storing this in an array, we should probably also store the capacity so that we know when to restructure and make a larger array. Since we'll actually have to go do that with an array, there's no easy array list resizing, or we'll have to write our own resize for this. So what does a constructor look like? We need to initialize the fields. So the next thing I should think about is making a constructor. A min heap. We'll start with just passing in a capacity and fill in the capacity, this dot capacity. The size of an initial heap should be 0. And we need to initialize this array. How do we want to do that? This is going to be a fun line to write. This is not a straightforward line because it's an array of T's. So how do we make sure that we size this to be appropriate? So the syntax we want will say, we're going to make this as basic as we need to, and then cast it into what we need it to be. So we're going to make a comparable array that is size this dot capacity, since we just filled that in. This is going to give me an error when I do this, but it's because elements is supposed to be a T array, and we've declared it to be a comparable. So the easiest solution to make sure this is a T, since we're not filling it with anything, is that we're going to cast it as a T array. So that will actually get it done. So we've made an array of T objects that at least now, since we make them comparable, knows that we can actually compare them. If we just made these T's, there would be nothing that would easily allow us to compare them. So this line will make it easy to compare them. Let's start with some of our easy methods this time rather than saving them for the end. So like with just about every collection, we just want to implement a size getter. So size will return the size. Is empty looks the same as everything we have. Every time we've written it, we'll just return whether the size is 0 or not. Now it gets into the fun stuff. We need to go implement some of our guts. So let's write insert. First of all, let's just write the insert's going to take a parameter. What kind of parameter is insert going to take? We will, instead of a value that we need to add to it, since we're writing this generically, that value is going to be generic as well. So we'll just pass in a generic data value. So how do we want to do it? What should we do first?
Well, you want to check.
Yeah, I think we'll be able to probably get that all in the same. The same window. Is there any possible error that we could run into? Yeah, you could pass in something that is null. That would be something that would not be great to try to put into our list. So let's throw an illegal state exception. So the first one of these, let's say if. So this would be a bad parameter. So there's one other thing for an illegal state exception, but. What kind of exception do we want to use? We pass in a bad parameter. Yeah. It is null from. One other one, the illegal state would be something like if the capacity is full and we're not planning to resize. So I'm not going to implement the resize logic, given that that's something that you've basically already done in one of your homeworks. I'm just going to throw an exception for now, but this is where that resize would go. So if the heap's value size is actually at the capacity, so if a call to size greater than capacity, then we could throw. Great, let's get into the logic. How do we insert? What do we want to do? When we inserted, where were we going to, where's that initial place for that insert is going to be?
We want to get down to the last row in the leftmost spot.
Yeah, where is that going to be in the underlying array that we are storing this as? The next available one, where would that be, given the way that we've written things so far? We separated that size and that capacity for a reason. The size or capacity? Size, yeah. So we can do that. Let's just say, let's immediately write elements of the size, since that's going to be the element we want to put it, is data. So if there are two things in our heap that says that the next index we want to access when we add something is index 2, since we're 0 indexed. First thing is at index 0, the second thing is at index 1, and this new thing should go at index 2. So that will get us there. Since we just put something in, size should grow. What else do we want to do? Have we potentially violated any heap constructs or any heap rules after we did that? Yes. Since this process may be used for something else as well, I'm going to write this as its own method. Heapify up. That is going to have us actually going through and comparing and doing that. So now that we've done that, let's actually write heapify up. Heapify up should not be public, should it? Doesn't actually take anything, it's going to work on this object. So this is going to rely on us successfully figuring out where our parent is. If we go back to the work that we did on Friday, thinking about where is, given this structure, where is the parent, where are the left child and right child? We're gonna need that logic to implement keep a phi up. So we're gonna start looking at where this element was inserted, which we know is at the element size -1. So that's the position of where the element we just inserted is. Since we just bumped up the size -1 will be the index where it is stored. We're also gonna need to keep track of a parent. So where is the initial parent of current index? What did we say that was? Yeah,
Current index -1 divided by 2.
current index -1/2. That is right, that is what we said. So now we want to loop some logic. We want to say something about this current position that we just inserted and the associated parent index. What is the stopping condition for this? We want to be able to compare the current value with its parent. If it's larger than its parent, swap them. If it's larger than its parent, swap them. If it's larger than its parent, swap them.
We just added the first current index -1 would be -1.
And -1 divided by 2 take the floor is still -1. No. Yep. So yeah, you probably want to check if it's the only or the first one. So size is 1 when we do this. So if size were 0 after this insert, I don't think that's possible. The only place so far that we've called keep a phi up is bumps up the size. And this size should never be 0 after we've inserted something.
The current index for a size of 1 is going to be 0, 0 -1.
Yeah. Yeah,
So it's going to
still have that issue in that one case. That's fair. Yeah,
If at that point the size is 1, you just have the root, you shouldn't need to do it by right? So you just
Right.
only if size is greater than 1, then you put by
yeah, then is there any reason to keep a phi up? Yeah, that's the easy way. And size greater than 2. Yeah. Cool, that'll work. What next? What do we want to do?
The array at the current index is less than, or sorry, is greater than the array at the parent index.
Yeah, so to do that, we actually have to invoke and use our compare to. So we're gonna check whether while the parent index. I think, yeah, this is what would catch the size is greater than 2 issue. You could check it here too. While the parent index is greater than or equal to 0. And so now we need to check elements of the current index dot compare to elements at the parent index. We need that to be what, greater than 0, less than 0, what should we say?
0.
So if that's greater than 0. We're doing a max heap or a min heap? We're doing a min heap. It should be less. So we throw that while in there, we're going to implement our own swap. We're basically out of time. So all that's left here is to swap the current index with the parent index. or swap what's at current with what's at parent, but that's what we'll do that. We'll implement that tomorrow, and then we just set the current index. The new value of the current index is the old value of the parent index, so we're making the current the parent. And then we need to recalculate the new parent index in preparation for the next pass through the loop. So then we would just say. And now instead of using current index for this, we'll use parent index, the old parent index minus 1/2. No, it's not. It's still the current index minus 1/2. That still prepares us for the next pass. Since we just set them equal to each other. So this is basically heapify up, which finishes off insert. We'll come back and finish this whole process off tomorrow. I'll have office hours starting now for most of you probably to get this thing working. So, for that.